over section 4.1, Detours and Midpoints. After studying this section, you'll be able to use detours and proofs and apply the midpoint formula. Looking first at detour proofs, to solve some problems it's necessary to prove more than one pair of triangles congruent. We call these proofs detour proofs. Looking at this example is an example of a detour proof. So I'm given that segment AB is congruent to segment AD, segment BC is congruent to segment CD. I want to prove that triangle ABE is congruent to triangle ADE. If I was going to prove these two triangles congruent, I'm only given that AB is congruent to AD. I could say that AE is congruent to AE by the reflexive property, but I don't have an angle, so I'd need this angle here, BAE, to be congruent to angle DAE if I was going to use side angle side, or I'd need segment BE is congruent to segment DE to prove the triangle is congruent by side, side, side. I don't have either of these, so I need to look at what other information that I'm given to see if I can get either that angle or that side. I have AB congruent to AD and BC congruent to DC. So if I look at these two triangles, I could prove these two triangles congruent because I have AC congruent to AC by the reflexive property, which would make these two triangles congruent, which would give me that angle that I'm looking for, BAE, congruent to DAE by CPCTC. If these two angles are congruent, then I could have my smaller triangle ABE congruent to the smaller triangle ADE by side angle side. My proof would look like this. I take a detour here at steps 2 through 4 to prove my larger triangle is congruent to get a piece of the smaller triangles. Now looking at procedure for detour proofs, first we want to determine which triangles we need to prove in order to be congruent to reach the required conclusion. Then we want to attempt to prove that these triangles are congruent. If we cannot, then we will use a detour. So in a detour, we want to identify the parts that we must prove to be congruent to establish the congruence of the triangles. Then we find a pair of triangles that we can readily prove to be congruent and contain a pair of parts needed for the main proof. We prove those triangles congruent, then we use CPCTC and complete the proof planned from step 1, the original triangle that we were trying to prove. Now looking at a review of the midpoint formula, remember midpoint is the middle point of two coordinate points. So in order to find the middle point of two coordinate points, I take the average of the coordinate points. So x1 plus x2 divided by 2 and y1 plus y2 divided by 2. Looking at a few sample problems, in problem 1 I have the following givens. I want to conclude that angle WQP is congruent to angle XQP. So this angle here is congruent to this angle here. In my givens, I'm given that line PQ bisects segment ZY, which would give me ZP congruent to YP. Q is the midpoint of segment WX, which would give me WQ is congruent to XQ. Angle Y is congruent to angle Z, and segment WZ is congruent to segment XY. Based off of these givens, I have that triangle ZPW would then be congruent to triangle YPX. This is the detour that I'll need to prove in order to prove angle WQP is congruent to angle XQP, because angle WQP is a part of this triangle here, where angle XQP is a part of this triangle here. If I was to prove that these two triangles were congruent just based off of my givens, I couldn't do it, because all I'm given is segment WQ is congruent to segment XQ. I could say that segment PQ is congruent to segment PQ by the reflexive property, but then I don't have another angle or another side. So by proving the two smaller triangles congruent, I could then use CPCTC to prove that segment PW is congruent to segment PX, which would prove my larger triangle is congruent. Then my angle WQP would be congruent to angle XQP by CPCTC. Looking at this in proof form, I'd have line PQ bisects segment YZ, that's a given. Based off this given, I have segment ZP is congruent to segment YP by the definition of segment bisector. Then angle Y is congruent to angle Z, that was given. Then segment WZ is congruent to segment XY, again given. Now my two triangles are congruent, so triangle ZWP is congruent to triangle YXP by side angle side. Based off these triangles being congruent, I can say that segment WP is congruent to segment XP by CPCTC. Then I have Q as the midpoint of segment WX. That was given. Based off this given, I have segment WQ is congruent to segment QX by the definition of midpoint. Now I have segment PQ is congruent to segment PQ by reflexive. Now my triangles are congruent by side, 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 so triangle WPQ is congruent to triangle XPQ. And now my angles are congruent by CPCTC, so angle WQP is congruent to angle XQP. Looking at problem 2, I want to find the coordinates of M, the midpoint of segment AB. Remember, the midpoint is the average of my two coordinates. So if I'm looking for the midpoint M, I'd take the average of the x coordinates, -1 and 7, so -1 plus 7 divided by 2, and then the average of the y coordinates, so 3 plus 6 divided by 2. -1 plus 7 is 6, 6 divided by 2 is 3. 3 plus 6 is 9, 9 divided by 2 is 4.5. So my midpoint of segment AB is 3, 4.5. Looking at problem 3, I have triangle ABC. I want to find the coordinates of the point at which the median from A intersects segment BC. Remember, median is a segment from a vertex to the opposite side that splits the opposite side into two congruent pieces. So BM would be congruent to MC. So M is the midpoint of segment BC. So I want to find the average of my two coordinates. In order to do that, I'd say 2 plus 6 divided by 2 and 4 plus 10 divided by 2. 2 plus 6 is 8, divided by 2 is 4. 4 plus 10 is 14, divided by 2 is 7. So my midpoint of segment BC is 4, 7. In this lesson we learned detour proofs are proofs that will require you to prove multiple triangles congruent in order to get enough information to prove your original statement. And the midpoint of two coordinates is the average of your x and y coordinates. That's a wrap on today's video. We'll see you in the next one.